Alright, this is lesson 1.1.1, Similar Machines, Lever, Wheel, Axle, Pulley. Alright, there are 6 similar machines, lever, wheel, axle, pulley, inclined plane, wedge, and screw. Mechanical advantage is ratio of magnitude of resistance and effort forces. Also, it is the ratio of distance traveled by effort and resistance force. Alright, so we want to know how much a machine can work it can produce. So we're going to take all these calculations we're doing in this lesson and determine the amount of work that a machine can produce. So, simple demonstration. The initial position and the final position force pushes the yellow crate across the plane, and the formula we're going to use is at the bottom there, force times distance equals work. Alright, mechanical advantage ratios. Magic number is 1. If you have an MA, mechanical advantage greater than 1, less force is required to overcome the resistance, and proportionally greater effort distance is required to overcome the resistance force. If MA is less than 1, a greater effort force is required to overcome the resistance, and proportionally less effort distance is required to overcome the resistance force. MA can never be less than or equal to 0. IMA, friction is not taken into consideration. Ratio of distance traveled by effort and resistance. Traveled by effort and resistance force. Here's your formula. IMA equals dE over dR. I'm going to keep the definitions up on the right as we go through the lesson, so you can quickly refer to those formulas. Okay. Distance effort over distance resistance is your IMA, and this is focused mainly on distance, while AMA is focused on force. AMA equals force resistance divided by force effort, and friction loss is taken into account. Alright, so if you have a mechanical advantage of greater than 1, you're going to be further away from the fulcrum, and it's going to require less force to overcome the resistance. An example of that would be windmill, ramp, and a can opener. That multiplies the input force. Real world mechanical advantage less than 1 would be, if you can think of something that takes more force to overcome resistance, that would be anything in a gym. You have to use more force to overcome the resistance. Alright, so illustrations or animations at the bottom. The middle one is both effort and resistance are in the same direction. Bottom left animation is mechanical advantage greater than 1. Your effort is on the outside of the resistance, and resistance falls in between fulcrum and effort. The animation on the right is going to have the resistance on the outside, effort on the bottom, and it's going to have a mechanical advantage of less than 1. Alright, so middle illustration, MA equals 1. You have a balanced lever, so your mechanical advantage is equal to 1. Illustration on the left, or equilibrium, I should have said equilibrium. Illustration on the left is your effort is close to the fulcrum. You're going to have a mechanical advantage of less than 1. And on the bottom right illustration, your effort is far enough away from the fulcrum to give you mechanical advantage of greater than 1. All right, and that was a first class lever. Second class lever is oh, let me back up real quick. You can have a mechanical advantage of greater than or less than 1 with the first class lever. It's important to know. Okay, second class lever. Resistance and effort are in 2 different directions. Mechanical advantage is always greater than 1. So you have your effort on the end, and your resistance is in the middle. All right, in this situation, your mechanical advantage is always going to be less than 1. Your effort is in between the resistance and the fulcrum. In both second and first class levers, the forces are in opposite directions. First class, they're in the same direction. All right, so before we get into IMA, AMA, and efficiency, we have to know our moments. A moment is magnitude of force times the perpendicular distance from the point. It's got to be perpendicular. Okay, moment equals distance times force, torque. So we're going to produce torque around that fulcrum with the distance of resistance pushing counterclockwise and clockwise. Lever moment calculation, we're going to calculate the effort moment, which is the left-hand side, and distance times force is 5.5 inches times 5 to 15 pounds, which equals 82.5 inches pounds. We keep both units of measurement. Now we're going to say, okay, rotational equilibrium is when all moments equal 0. Rotational equilibrium is when clockwise and counterclockwise moments equals the sum of all counterclockwise moments. Let me back up. Clockwise and counterclockwise moments equals the sum of each side. All right, so lever moment calculation. We have a missing variable on this side of the lever. We've got everything over here, and we already did this in the previous slide. 82.5 inches pounds equals 36.66 pounds times dr. We don't have the dr. Distance resistance, we're missing that. So we're going to divide both sides by 36.66. And it's going to be 82.5 inches pounds divided by 36.6 pounds. Pounds are going to cancel each other out, and you're going to be left with inches. And so 2.25 inches is your dr. So rotational equilibrium is, may not have said this clear first time, but effort moment counterclockwise equals the resistant moment counterclockwise. So lever IMA, your effort circumference is outer circle. The resistance circumference is the inner circle. And we are going to look at IMA as the effort arm length and resistance arm length. Okay, so lever AMA, the ratio of applied resistance force to applied effort force. So force resistance is going to be 32 pounds divided by 16 pounds. Units of measurement, pounds, cancel each other out, and you're left with AMA of 2. IMA equals distance effort, which is 5.5 divided by dr, which is 2.25. And that's 5.5 divided by 2.25 inches. Unit measuring inches cancels out. And you got a 2.4 on the IMA. And there's a couple reasons why this is the IMA is larger than the AMA. You just have to put all the information together and come up with your own answer on that one. All right, efficiency in the machine, the ratio of useful energy output to the total energy input, or the percentage of work input that is converted to work. All right, so the ratio of AMA to IMA that's going to be your efficiency. AMA was 2. IMA was 2.44. And so we're going to divide 2 by 2.44, multiply by 100. 82% was the efficiency of that lever. No machine is 100% efficient. All right, we're going to switch to wheels and axles. The wheel is a simple lever to lift or move an item by rolling. Can you think of an example of a wheel driving an axle? It would be a car wheel, laundry, dial, and faucet. All right, so the wheel axle IMA is distance effort, distance resistance. Depends on if the axle is driving the wheel or the wheel is driving the axle. I think we're going to do both examples here. What is the IMA of the wheel if the axle is driving the wheel? So the effort is going to be purple, resistance is going to be blue. So it's going to be 6 divided by 20, which equals 0.3, and then we just move the decimal 1 to the right, and that's a 3 to 10 ratio. What is the IMA of the wheel if the wheel is driving the axle? So then we're just going to switch the value inputs, and it's going to be 20 divided by 6 equals 3.33, and we're going to we'll switch to AMA, force, and what is the AMA if the wheel is driving the axle? So the effort is going to be 70, and the resistance is going to be 200. So 200 divided by 70 is 2.86. What is the efficiency of the wheel and axle assembly? AMA, 2.86 divided by 3.33 times 100 equals 86%. We'll switch to pulleys real quick. The pulley is used to change the direction and magnitude of force exerted by rope or cable. The illustration on the right has a fixed fulcrum center of the axle, and it has an IMA of 1. Change the direction of force, and the illustration on the left has a switch the fulcrum to the left-hand side of the pulley, and the strand is attached to the ceiling, so the pulley is going to move, and it has an IMA of 2. Pulleys in combination, mixed and movable pulleys in combination. If a single rope or cable is threaded multiple times through the system, number of pulleys equals number of strands opposing the force of load. So in this case, we have 1, 2, 3, 4 strands opposing the load, which is the motorcycle, and so we have an IMA of 4. Compound machines, if one single machine is used with the other, we have a lever pulley system. IMA of the pulley is number of strands, which is 2. Distance effort is 12. Distance resistance is 4. 12 divided by 4 is 3. 3 times 2 is 6. So our IMA total is 6. Pulleys in combination. What is the IMA of this pulley system? 1, 2, 1, 2, 1, 2. 2 times 2 is 4. Times 4 is 8. Pulley AMA. AMA is force resistance, force effort. Force resistance is 800 divided by 230. Force effort was 230. Units of measured in pounds cancel out, so we got 3.48 is my AMA. What is the efficiency of the pulley system? AMA is 3.48 divided by 4 times 100 is 87%. All right, angles don't matter. That's a misconception. Angles do matter. We're going to get into the illustration at the right later on in this school year. This is going to deal with determining the angles of the left and right here, and that's going to be for another unit. We're just dealing with parallel and perpendicular resistance forces, and in this case we're just going to look at this pulley over here. It's just got 2 strands, and so the IMA is 2. Count the effort strands. If it pulls up sometimes, It could pull it sideways, depends on how you got the ropes and what you're picking up. Pulley IMA, number of strands opposed to the load. Kind of strand if it opposed to the load, or the load's moving a pulley, it might pull up or down. Alright, so that concludes lesson 1.1.1, simple machines, and this is one of two of the videos for this section.